Greetings, Algebra Express. We are in Rockswold 4.2 today. We are going to go over polynomial functions and models. So they start with defining what a polynomial is. And so they say that this section is polynomial language. So they're going to put it in some math language. So the definition of a polynomial is a sum of terms of the form ax to the n. So it is something that has a x variable on it. Or constant where a is a number. And n is typically used for natural. An odd thing is some people include zero in the natural numbers, some people don't include zero in the natural numbers. Some people differentiate the natural numbers from the whole numbers by including zero or not including zero. So typically I don't include zero, but they do. And so if we're looking at this, they give an example of a function f of x. 5x to the 18 plus 7x to the 12 minus 12x to the 7 plus 2x to the third minus 4. And you might be looking at this, and I said everything should have an x on it. And we see that this 4, you might look at this 4 and say, well, it doesn't have an x on it. But if I wanted to put one there, I could always put an x to the 0 power. So that's where the zeros coming in. We can have constants on there. We can add or subtract a constant number after all our x variables. So basically there's an x variable, there's a power on it, and there's a coefficient out in front. That coefficient can be any real number, and the exponent has to be a natural number or a whole number. Okay. So they give us a few functions and they want to know if they're polynomials. And then if they are polynomials, can we give a degree and a leading coefficient? Okay. So if we're looking at this, this looks like the square root of x plus 2. So we've talked a little bit about this, but if I wanted to rewrite this with exponents instead of a radical, how could I do that? X plus 2. And when I do a square root, it's like I divide by 2, or it's like a 1/2 power. And if I write this as a 1/2 power, I want to know if this is a polynomial or not. And I'm trying not to just give it away right quick. But if I'm looking for a polynomial, I have to have variables. This x and this plus 2 look good. But when I look up here at this exponent, I have an exponent of 1/2. And even if I do some distribution here or something, I'm not really sure exactly how that's going to go. That's not going to go too smoothly. That'd be something complicated. But there is a 1/2 power on this variable. And so since there's a power on the variable, it is not a polynomial. We have to have natural numbers in our exponents. So the degree and leading coefficient, I'm not even going to mess with it if it's not a polynomial. This thing as well, we might be able to write it another way that might be more helpful. Do minus x to the third plus 5. The other way, oh, that's not an x to the third, that's an x squared. Sorry. So if I actually write this thing and the correct order, it might help. Because this is an x squared, this minus 0.6, that's okay, that's a real number. The thing that might be throwing you off is this pi. So the pi doesn't have an x, but if it doesn't have an x, we can write x to the 0. So if this constant coefficient something like x to the 0 if it really makes you feel better. So this doesn't fit our definition of what a polynomial is. So pi is a real number, so this is okay. The degree. So when we talk about the degree of a polynomial, we are talking about the largest degree that the polynomial has. So this is a second degree polynomial. The leading coefficient is the coefficient on the leading term when we write things in descending order. So the leading coefficient here is the minus 0.8. Okay. Now look at this next function, m of x equals 2x squared minus 1 over x. We talked about 1 over x. So if I want to write that with an exponent, 1 over x is like 1 over x to the first power. This is like x to the... If I'm looking at this, this looks like 2x squared minus x to the minus 1 power. Is this a polynomial? So 2x squared fits the definition, minus 1x. The minus 1 is the thing that does not fit our definition. So it cannot be a negative number as an exponent. So this is not a polynomial, and I don't want to worry about the rest. N of x equals 3. So this is like a constant function. And if we don't see it there, we can always think about it as there's no x's there, or x to the 0. And so is this a polynomial? This is the degree. What did I see there? Is 0. Okay. And the leading coefficient is the thing in front of the variable, which is the 3. Okay. So we talked about polynomials larger when we were talking about quadratics. So now we've bumped it up to larger polynomials. And now we want to talk about drawing piecewise functions with larger degree polynomials. And so we've already done piecewise functions. So we talked a little bit about that before, but as a quick sort of recap, I have two sorts of things that I'm looking at here. So I'm looking at one function y equals x squared, and a little simple at y equals 3. So I want a solid dot on this one where x is equal to minus 4. Solid dot, x equals to minus 4. And I want an open dot at x equals 2. And then the other one is a solid dot at x equals 2. And I believe it's a solid dot at x equals 8. So these are the points that I want to graph, or I'm getting at the points. So I do have to fill things in a little bit. So if I fill in a minus 4 into this, this looks like 7 minus 16. Gives me a negative 9. So the point here, and I'm doing the same thing with the 2. 4, which will give me 3. And so the other point I want is 2, 3. Okay. And then I have this one at x equals 2, and my y is 3, at x equals 8, and my y is 3 there. So that one should be a constant, that one should be a flat function. So hopefully when we get to graphing these things, it looks like that. So I want to jump back to the graph and plot these points I just found. So I'm going to plot these points at a -4, -9. Solid, -4, -9. And then there's one open at 2, 3. And then the other one picks up at 2, and I'm going to line here. But I want to think just for a minute about how to do this. Y equals 7x squared. I draw a straight line. This is not a straight line. This graph is not a straight line. It is a square function. It's a quadratic. It should look like a parabola. It should have a little curve to it. So we have to think about what this curve is going to look like. If you want, it might be more beneficial to -x² plus. So if I write it in descending order, it might actually help me to think about what this thing looks like. Positive, the parabola, it goes up. If it's negative, it goes down. So this is looking something like that is what I have in my head. It's an inverted parabola. Ooh. And it goes through 7. So we do have to account for the vertex. It's a negative parabola raised up 7. 1, 2, 3, 4, wait, 1, 2, 3, 4, 5, 6, 7. So there is a vertex right there. It is turning around. Okay, so now we want to draw this parabola up to the vertex. Horribly turn, but there is my sort of rough sketch of this thing. Okay, so to be honest, I forgot they give you the vertex in this one. Sometimes they will just give you like a piece of this parabola, right? And so we still have to be able to draw it sort of curvy. It can't just be sort of like a straight line between these things. Have a little bit of curve to it. It's probably not drawn very well. A bit of curve of this. A bit of a curve of this. So if you draw it as a straight line, you're probably not going to get full credit for it. Okay. So before I go to the next screen, or before I go to the next page, I want to do a screen share. And I want to show you a few things on the Desmos. So this is what your graph should sort of look like. So this, I know they give you a long span. And so if it was zoomed in a little bit, it would look a little differently. We would have to account for this curve here, right? If I had just a point from here to here, I would have to draw this curved a little bit. So you'll have to account for the curve of the parabola. This isn't the best graph to really do it on, to be honest, because this is a long stretch here. And it's kind of hard to draw this curve a little bit. But this is what it should look like. And then there's one other question I want to ask, is this continuous? So is this a continuous graph on its domain? So if we look here, if you remember, continuous means you don't have to pick up your pencil when you draw it. So the main point that was maybe a point of interest was this 2, 3, but this one picked up where the other one left off. And so this is absolutely a continuous function. Okay, so the next thing I want to go to is, where am I at? That's good. I want to look at even functions. So if I start with, or sorry, not even, odd. So these are odd numbers. So if I'm looking at odd number functions or odd degree functions, when we talk about the degree of the functions, what we're referencing is the largest degree there. So if I'm looking at an odd degree function, so the first odd degree function is x to the first power, or just x, y equals x. So that's a line. That's that line going right down the middle if you just do y equals x. Also known as the identity function. So if we do y equals x to the third, you might notice it has a squiggly, but the end behavior. So if we look at what's happening off here, so as we go off to minus infinity with the x, this function is also dropping down in the y. The y is also going to negative infinity. So if we look at their end behaviors, on the ends, it's doing the same thing. Maybe zooming in might be a little bit. They look like they're going way off. So the x to the third is obviously increasing way more or decreasing way more. But it's doing the same sort of thing. It is at a different rate, but it's doing the same sort of, it's going in the same direction. Same thing with x to the fifth, right? It's a little bit sharper, but it's still going off in the same direction. X to the seventh, same thing. And then there are, so we talk about the degree of the function as the highest degree. So I can absolutely go throw in some, let's just do 3x to the 6 or something. I can go throw in other stuff. Let's do a half maybe, so it's not quite as, it really picks it up. Okay. I can go throw in lower stuff. It's not going to change the end behavior very much. It's going to basically make it more or less squiggly, right? It gives it more squiggles. Extremely technical term, right? But that's what these lower terms do. They're not really changing this very much. The end behavior on this is still the same. So that is if we have a odd degree polynomial. So the largest term here is an odd degree. Same thing with these. I can go in, throw in an x squared minus x plus 1 or something, right? My end behavior on these things is not going to change. If I throw in a negative sign in front of this, so if the leading coefficient is negative, then my line flips. So now I have a negative line with a -1 slope. And if I do the same thing to each one of these, I throw a negative in front of each one of these, the end behavior of these is now flipping. So now they're going the opposite way. So these are really complicated. But if we want to think about the end behavior of an odd degree function, the easiest odd degree function to think about is y equals x. So if it is a line, or if it's an odd degree, it's going to look like a line with its end behavior. And if it's got a negative leading coefficient, it's going to look like a negative line with its end behavior. So these are the two pictures you should have in your head if you think about an odd degree function. Is it negative leading coefficient or positive? That will tell us the end behavior of the graph. Here, we want to talk about even functions. So if we think about even functions, the lowest even function you can think about probably is y equals x squared. The next thing looks like y equals x to the fourth. You notice it looks very similar. I could do the same thing, y equals x to the, what, 6? I could add some small stuff in there. It's just going to make it more squiggly, right? But we're still going to get the same end behavior. So it's coming in and going out on the same side. So if it's positive, like a positive parabola, it is going to come in and go out to positive infinity. On the left, it's going to shoot off to negative infinity. On the left, when we go off to negative infinity, it's going to shoot up to infinity. When we go off to positive infinity, this is going to shoot off to positive infinity. If we throw in a negative in front of it, what does a negative leading coefficient do? It flips it. It's going to go the other way. So I'm thinking, when I'm thinking about even degree functions, the picture that I really want in my head is not those. It's just the parabola, right? I just want to think about, what is a positive parabola? What does a negative parabola look like? That's what my end behavior on these guys is going to look like. So there's more squigglies in the middle, right? But just looking at the end behavior, what it's doing as we shoot off to infinity. What's it doing off there? Boop, 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 boop. Okay, sorry. Where's my stop screen? There we go. Lost control. So that is the end behavior. Oh, one more thing. Let's go back. Turning points versus the degree of the function. I want to talk about that. So if I start off with y equals x, there are 0 turning points. That is a 1 degree function. If I do y equals x squared, there are 1 turning point, and this is a 2 degree function. Let's do x to the third and see how many turning points that guy has. Well, not too many, but if I add some other stuff in there, well, let's do. If I talk about a 3rd degree function, there can be 2 turning points in there. And if I talk about a 4th degree function, ooh, there's too many lines. Do it. Let's see how many squigglies I can get. There we go. So if I talk about a 4th degree function, I can get 3 turning points in there. So we can have less turning points. That's absolutely a thing that we can have. But if I have 3 turning points, I know I have at least a 4th degree function. It could be larger. So if I'm looking at the relation between turning points and the degree of the function, I take the number of turning points and I have to add 1 to it to get the least degree function that I can work with. So that's the sort of relation that's happening there between turning points and the degree of the function. So that's something that they try to throw out at you. They're like, here's a degree 3. Well, we see there's 2 turning points in there. Really, the way you want to think about it is 2 plus 1 is going to be at least. It could be more. But it is definitely an odd degree. It could be 5 degree. It could be 7 degree, right? But we need at least 3. Same thing here. If we count 3 turning points, I did 3 plus 1 and figure out it's at least a 4th degree. Okay. So this is relating turning points to degrees. So if we take the turning points and we add 1, we get the least degree. So this is at least a 4 degree. It could be more, right? It could be 6, it could be 8. the leading coefficient is positive or negative, or n is even or odd. So this is what I was doing previously. So if we have an even function, so it has squigglies in the middle, but the picture that we think about is either a positive parabola or a negative parabola. It has squigglies in the middle, but let's ignore this picture I have in my head. So that looks like a negative parabola, that looks like a positive parabola. So if the leading coefficient is positive, it looks like a positive parabola. If the leading coefficient is negative, it looks like a negative parabola. So I know this thing has squigglies in the middle, but I'm ignoring this. The picture I have in my head looks like this, or it looks like this. This is a 5-degree function. This is photos I went over, and the Desmos, the first set after that piecewise at least. So if it is positive, it looks like a positive line. If the leading coefficient is negative, it looks like a negative line. So the end behavior, when you think about end behavior, don't think about all the squigglies in the middle. Think about either a parabola or a line. Okay, so they say, okay, so they're doing this backwards. If we have at most n x-intercepts, at most n minus 1 turning points. So if I'm doing a degree 3, I have at most 2 turning points. If I have a degree 4, I have at most 3 turning points. So this is the same thing that I was saying. We have at least a degree 3. They're saying this a little bit backwards from what I said. So instead of saying at least with the degree, they're saying at most with the turning points, which is looking at it from the other perspective. Same picture, just a different perspective, right? So these turnings only happen when we add like the smaller degrees in there. So if we think about y equals x to the third, it has 0 turning points. So that might be a good example to contrast that to. So we want to look at the number of turning points here. So if we're counting the number of turning points, that's the first thing they ask us. This is a turning point. There are 3 points where it goes from up to down and from down to up. Sign of the leading coefficient. So this thing is going off that direction. So the first thing I think about, does this look like a parabola or does this look like a line? And so if it's going off and coming in at the same side, that looks more like a parabola than a line. So parabolas come in and go out on the same side. Lines come in and go out on opposite sides. So this is coming in and going out on the same side. This looks like it is going to be an even degree function. And the sign on it would be that it is a negative even function. So this looks like an inverted parabola. So this should the number of x-intercepts. So now we're looking at our x-intercepts. So it hits 1, 2, 3. So let me get a different color, maybe highlight it, do some red over black. Those are my x-intercepts. There are what is the minimum degree? So if I have 1, 2, 3 turning points, the rule is I have to do 3 plus 1. Degree function. I should not do that in red. I should re-emphasize turning points plus 1, right? Let's do it in black. That is the same thing as this number, right? This 3 is this 3, not the other 3. I'm doing number of turning points plus 1 to get the minimum degree. Okay. On the next page, we have a similar exercise. We want to count turning points. We want the sign of the leading coefficient. Should have asked us whether it was positive or odd or even. Okay, so whether something is odd or even, and this is a bit of a weird word, but I believe it's called parity, right? Can you put them in pairs? Okay. Number of turning points here. We want to count turning points. So have arrows going off. And the notes, they don't put arrows on there. Desmos doesn't put arrows when you do a graph. So if there's not arrows in general in this class, you could probably assume that we want there to be arrows there. So number of turning points, we want to count the turning points that are happening here. Every time it goes up and down. There are 1, 2, 3, 4 little turning points. Okay. Sign of the leading coefficient. So now we want to think about, is this an even degree function or an odd degree function? And again, like I'm using even degree function. I made like a really big emphasis when we went and learned those symmetries, even and odd symmetry. Even and odd symmetry is not the same thing as even degree function or odd degree function. So if I want to look at this, is this an even degree function or an odd degree function? Does it look like a line or a parabola on the end? And it goes up. Goes down and up. Those are opposite directions. This is looking like a line. This is an odd degree function. So I think about an odd degree polynomial. Does this look like a positive or negative line? Is the next thing. So we want the sign of the leading coefficient. So this absolutely looks like a line. I'm going to say that looks like a positive line. The number of x-intercepts. So now we're looking at where does it hit the x-axis. It hits it in 5 different spots. There are 5 different x-intercepts. Okay. The minimum degree on this thing, again, we have to take the 4 and we have to add 1. So there are 4 turning points, so at least a 5 degree function. There is another thing that indicates we need at least a 5 degree function. We are getting 5 x-intercepts. We talked about that with quadratics. In the next section, we'll talk about it a little bit more, I believe, and talk about real zeros of polynomials. But this is giving you solutions, right? So if we're getting 5 solutions, guess what? We need a 5 degree. But look, I got 1, 2, 3 solutions. I need at least a degree 3. Well, at least I need a degree 4 here because it has 3 turning points. So what is that telling me? I'm expecting 4 solutions because it's a degree 4, but I'm only getting 3 of them that are real. Oh, I don't know what that other one must be. Okay. So now they want to give us a sort of word problem and put our newfound knowledge to use a little bit with something, with an application. So new construction building permits per year, and X is the year, Y is the number of permits. Suppose you want to come up with a polynomial function to approximately model this data. What degree polynomial would you recommend? So if I'm being honest here, this kind of all depends how you sketch your graph. So I'm going to sketch a graph down. Sketch a graph. Looking at 1, 2, 3. That's one graph pretty rough. 1, 2, 3, 4, 5, 6, 7, 8 turning points. So I'm getting like 8 turning points. So I got 8 turning points. I want to do 8 plus 1 gives me a 9th degree function. I have to recommend probably at least a 9th degree function. You may not have made yours quite as curvy, and that might be fine. You might say something less. You might say something more, right? I don't know if you really could put any more in there. I think it's about as many as you're going to put. But you might have made it a little less accurate, right? You might have just went up here. You might have just went down and up. Looking at the end behavior, it should be an odd degree function though, right? Okay, so now these are some things, and they will probably make you think a minute about them. But they want you to sketch these graphs, and I would highly recommend doing this in pencil. They give you a lot of information, and you kind of have to follow it, and we kind of just defined all these things, and now they want you to start sketching these things. So we want to do a degree 3. It's got a negative leading coefficient, and it's got 1 x-intercept. So if it's a degree 3, what this is telling me is it's odd with a negative coefficient. So I have those series of pictures, but when I see degree 3, if it's an odd function, I'm thinking of a straight line. So this is telling me a straight line with negative leading coefficient. So a straight line that goes downward is what this is telling me. So it's going to shoot up here, down over here. So what I'm going to do is I'm going to draw the end behavior on there first. I want 1 x-intercept. There are a few ways to do this, but this is a degree 3. So if you draw this as a straight line, that is not the way a degree 3 function looks like. If you wanted to do a little degree 3 south sort of thing happening, you can do that. If I'm doing this, I'm probably going to do x-intercept once, and I don't want to draw it completely straight. I'm going to draw it around, but I don't want to hit the x-intercept anymore. I just want to do one little squiggle. Up and then back down. And so I have 2 turning points. This is a degree 3 function. And I've gone through the x-axis once. And there are multiple ways to draw this. Like I said, you could go that's also degree 3, but you have to put that little leveling thing in there, right? And it's got 1 x-intercept. So there is no one sort of right definitive way to draw these things. You could have put the squiggle up here and done the squiggle and then came through the x-axis. But the thing is, you don't want to put more than 2 squiggles in a degree 3, right? Okay. So definitely go back through your picture and make sure it follows the things that it's giving you after you've drawn it. So we want a degree 4. So this the first I see that it is even, I want to think about this thing is a parabola. This thing looks like a parabola. Is it up or down parabola? That's the next thing they're going to tell me. It is a positive leading coefficient, so I'm thinking upward parabola. Right away, that's the picture in my brain. So it's going to come in and go out, going upward. There's squiggles in the middle I got to count for. So I have 3 x-intercepts. If I go through and come back through, that's giving me 2. And if I go back through and come back through, it's going to give me 4 x-intercepts. So I don't want to go through all the way. So how do I do that? One thing that might be a little challenging, but I did it and I turn back around. So then I have 1, 2, 3 x-intercepts. So I have 3 x-intercepts. This is a degree 3, which means it has one, or degree 4, which it means it has 1, 2, 3 turning points. It is positive leading coefficient, meaning both of these things are going up like a positive parabola. Okay. And so here's some student practice. So hopefully you're trying these out on your own. Degree 5 with positive leading coefficient and 3 x-intercepts. Okay, so degree 5, when I think about degree 5, I look at, is that odd or even? It's odd, so this should look like a line. It's got a positive leading coefficient, so it should look like a positive line. So it should be going out there from the bottom. Okay, my end behavior should look like a positive line. I have 3 x-intercepts. So we have done this before, but I want and if I go through and don't come back through, that gives me 3. Okay, and there, like I said, there's a few different ways you could draw this. So I have 1, 2, 3, 4 turning points. That gives me degree 5. The positive leading coefficient tells me that this looks like a line going positive line, and then the 3 x-intercepts. I have 1, 2, 3. And so, like I said, there are a few ways to draw this. I guess we could have went like 1, 2, 3, not like that. I think that also gives you a viable picture. There are 3 x-intercepts. This is a 1, 2, 3, 4 turns, which makes it a degree 5 positive leading coefficient. That's also a good picture. You could do that. So there's a few ways to get these pictures, and none of them are more correct than the other, right? They're all equally valid. So degree 4, when I look at degree 4, I'm asking myself, is it odd or even? It is even. So the second I think it's even, I think this thing looks like a parabola. So I'm thinking about my parabola. I'm thinking about a negative parabola is what the next picture is giving me. So I'm thinking about a negative parabola. This thing's got to go down. Going down and down. There are no x-intercepts. So if I wanted to draw a single parabola, that would be like a degree 2. But I would draw maybe just a curve just to indicate I got 3 turning points, and that this is a degree 4. So it has no x-intercepts, so it means it does not hit the x-axis. So it's got a squiggle and never hit the x-axis. I want a degree 2, so this is a quadratic. It's got a negative leading coefficient and 1 x-intercept. Woo, boy, I hope y'all can get this one down. So it's got 1 x-intercept. So if I go through and come back through, that's going to give me 2 x-intercepts. So I got to do the trick of where turn back around. So it's only hitting the x-axis once. It's hitting it at its vertex, right? And it's turning back around. degree 5. So I'm looking at this thing, it looks like a degree 5. So the second I see an odd degree function, I'm thinking this thing looks like a straight line that is a negative straight line. So that is a line going down. So it looks like it's going up here, it's going down here. That's a negative line looking thing here with one x-intercept. So I could squiggle it a few times, but I want 4 turning points. So I'm going to go through this is using one x-intercept. Now I'm going to do my turning points 1, 4, and again, you could do these squiggles anywhere you want. You're basically going through the x-intercept or x-axis once. It's a degree 5, 1, 2, 3, 4 squiggles. Negative leading coefficient looks like a negative line. Okay, and that's the final picture of these notes. Y'all take care, and I will see y'all soon.